Another way to look at this phenomenon is by seeing what happens if you have a magnetic field. Let's say magnetic field is going to the page and uniform, and you have a piece of wire. Let's say it's a conductor, length L, and magnetic field is B. This piece of wire has a length L, and it's moving at speed v, velocity v, in the perpendicular direction to the magnetic field. What happens if we move this piece of wire in the magnetic field? It has electrons inside. It has charges. When you move the electrons inside the magnetic field, what happens? What happens to the charges? Do they feel a force? Which way the force would be? If the charge is positive, your V cross B is up, right? But if the charge is negative, the electrons move down. The same as the positive charge is moving up. The electron moving down, positive charge is moving up, and this side therefore becomes negative, this side becomes positive, right? This side gets a little bit of negative charge, this side gets positive charge. Do all electrons go this way? Because there's a force acting on them, right? What happens then? Some electrons go down, or some positive charges go up, and then when they separate, they create their own electric field, right? So this migration happens until the force of magnetic field and force of electric field balance each other. For example, if the positive charges go up, they create an electric field from positive to negative, and there will be a force, electric force, downward, and magnetic force on positive charges is up, and this is F of magnetic field, and this happens until electric field applies the same force the other direction. And you know when that happens, right? If you have a charge Q, V times B, because they are V and B are perpendicular, QVB is the magnetic force, should be equal to Q times E. So the electric field that is created in equilibrium is equal to V times B. So E is equal to V times B, and it's downward. And what is the potential difference now if you have a uniform electric field inside the rod? What is the potential difference between one end to the other? Remember the relationship between electric field and potential difference? Delta V was negative integral E dot EL, right? And then if E is downward, means that if you go downward, you go to lower potential. Means that this becomes a little bit higher potential than this, and delta V will be E dot EL. And E is uniform, so it comes out, delta V becomes E times L. So there will be a voltage, delta V, equal to E times L. Now in this case, the upper part is positive, lower part is negative. But then E is V times B, so delta V, the voltage created will be B L times V, or BVL. Because it's created by motion, they call it motional EMF. And usually they denote it by E, clearly E. E will be B L perpendicular times B. BLV. So if the three V and B and L are in perpendicular directions, BLV. And it's called motional EMF, electromotive force. Electromotive force. This is completely consistent with this Faraday's law. Another way you can look at it, if you consider this as part of a loop. Let's say there's a rail here that's conductive, and then this is moving on these rails. And the flux through this is changing. This is a loop of wire. The flux through it is changing, and because of change of flux, you have EMF around the loop. And if you look at it like that, you can also say EMF around the loop is equal to d phi d over dt. How much is rate of change of flux through this loop? Because the face of the loop is perpendicular to the magnetic field, you can say this is B of the flux will be B times this area, right? This area here. B times the area over dt, and therefore E is equal to, because B is constant, E comes out, becomes B times dA over dt. But dA, if this is x, this distance here is x, and this side is L, area will be x times L, right? So B times d x times L over dt, and L is constant, comes out, E becomes B L dx over dt, and dx over dt is V. So it becomes dLV. Right? So this is consistent with that, but if you take this as a part of a loop. And the Faraday's law also gives you the direction of this EMF. How do we decide which direction the current or EMF in the loop would be? We say that it is in the opposite direction of change of magnetic flux. Flux is which way? Is into the page. Is it increasing or decreasing? It is decreasing, right? Because the area is decreasing. The field is constant, so the area decreases, the field is into the page and is decreasing. So the EMF should support that, support the flux. So it should be in a way to create its own magnetic field that supports this magnetic field. Therefore, it creates a clockwise direction EMF, which is sending positive charges up, going this way.